Thank you. Thank you, Mukesh, for the introduction. Very generous and very kind. And thank you for the invitation and for being here today. I'll focus this talk mainly on the nexus between water and food with some ramifications to energy. And the goal is that to see some of the interdependencies of this system, and also to go towards the end of the talk to look at the way in which the needs of water for the environments and for humans can interact and sometimes be in competition with one another. And so I always, when I talk about this topic, I always stress the fact that most of human uses of water are for agriculture and for the production of food. And so this is important because many people, when they talk about the water crisis, they think about people going thirsty. Instead, it's about people going hungry before being thirsty, because it takes much more water to fulfill our food needs and our drinking needs. And the water used in agriculture is basically of two different types. We use water in the rain-fed agriculture, so without adding additional water that comes from precipitation. Part of the water that we provide to agriculture is through irrigation. And so if we now look for a moment at the water flows from continental land masses, the water leaves these land masses in two different ways, either as surface and groundwater runoff, so in the liquid phase, or as water vapor, as evapotranspiration. So the former has been named a few years ago, about 20 years ago, by Folkenmark as a blue water flow. Instead, the latter one have been defined as green water flows, mainly because they are strongly mediated by vegetation. And so the water that is in the root zone above the water table is a green water stock, because it's the water that is accessible to most plants. Instead, the water in aquifers, rivers and lakes, and surface water bodies are blue water stocks. With the irrigation, we take some of the blue water stocks and we apply them to agricultural land to be turned into green water flows. And this is not much water. So if you look at the global evapotranspiration from land masses, is this big number. Part of it is taken by agro-ecosystems, partly by natural ecosystems. Natural ecosystems are not irrigated. So, and only this tiny blue part is the blue water flows that become, so green water flows is turned into evapotranspiration through irrigation. So it's a small part of the water evapotranspired by continental land masses, but it's very important because of these withdrawals for irrigation. We have rivers that are dry. The Colorado River is an example in the United States. We have basins of internal drainage that are becoming with lakes that are shrinking, like Lake Urmia in Iran, or the Aral Sea, or Lake Chad, or other examples around the world. And then we have groundwaters that are strongly depleted. So there is a big interest in this amount of water because it's small globally, but it plays an important role to sustain food security. About we see that 20% of the land, cultivated land, is irrigated. It contributes to 40% of the food, and it has also some environmental impacts. Years ago, we did this analysis. So we looked at the irrigated areas around the world, and where to meet the irrigation, the crop water requirements with irrigation, we have enough water to make it happen. So whether the water consumption for irrigation exceeds or not the available water, which is calculated as the local runoff minus the environmental flows, which are a fraction of the runoff. So we divided the world into tiles of, I think this analysis was done 50 kilometers by 50 kilometers, and we did a water balance analysis to see where this condition is met, which means that irrigation is unsustainable because it happens at the expenses either of environmental flows in streams and rivers or groundwater stocks. And so in pink in this map are all the areas where irrigation is unsustainable. And here I will refer to sustainable or unsustainable based only on this water balance. And clearly the runoff is cumulated down in the downstream directions, accounting also from upstream contributions. And there are other aspects of unsustainable irrigation related to salinity, related to the fact that the dams have environmental impacts, related to many other aspects, consumption of energy, etc., that are not captured. This is just sustainable or unsustainable based on a water balance. And about 40% of irrigation in the world is unsustainable. So it means that in the long run, will not be sustained because of this groundwater depletions. Look at the case of northern India, which is a typical example, but also the Great Plains regions of the United States. There is a lot of unsustainable irrigation. And this is an important point because when we connect to the problem of food security, if you talk to economists, they will tell you food security is not a matter of availability. There is plenty of food produced in the world every day, which is true, but much of it is produced unsustainably in the sense that even just hydrologically there is a depletion of water resources. And so there is an increasing demand for food in the world that is driven by the growth of population, then also by a growth in per capita consumption of food, not only in the calories that each one of us eats, but in the type of food. And the reliance on meat is associated with a stronger impact on the pressure on natural resources, including water. And then there has been an increasing demand for water by the energy system. For example, the case of biofuels. So if we look at the, I like to, when we start with the population growth, clearly the population is growing in parts of the world where the per capita consumption is very low, but we see that the growth in population has been accelerated in the course of the last 150 years because of major transformations in the system of production, and they have some important implications also for water. The Industrial Revolution is the first big acceleration. You see, it took the history of humanity until the early 1800s to reach 1 billion, and then in less than 120 years we had a 2 billion people because of mechanization, because also ability to expand irrigation to areas that were not suitable for gravity irrigation systems. Then the Green Revolution, also with fertilizers, crop improvements, and also additional irrigation, led to an unprecedented increase in the production of food, to the point that part of the food was used as a feed for livestock. And then we saw in the last 40 years an increase in global trade, which allows some parts of the world to depend on food produced in the other parts of the world, until we reached some major food crises in 2008 to 2011, which were the first global food crisis since the Green Revolution, which led to another idea of increasing crop yields in parts of the developing world where some of the innovations have been lacking, with some important implications for also local economies and livelihoods. And then we were talking about an increase in per capita consumption. Meat production requires 4 to 8 times more water per calorie than plant food. And a common pattern in the economic development is that as countries become more affluent, as can be represented by the average income per capita, we see an increase in consumption of meat. And so an increase in pressure also on the water system. And this would be, for example, the trajectory of China in the last 40 years. And so this means that there is an increase in demand also of water resources for the production of crops that will become feed for livestock. The energy sector, in proportion, uses much less water for irrigation, but locally can be very important, and we will talk more about it. Particularly, I think it's one thing I always like to stress is that the water used for the extraction of fossil fuels is usually calculated in terms of water in the in the extraction process, but it doesn't acknowledge the fact that those fossil fuels were come from biomass. There were plants that existed many millennia ago, and so they required some water for their growth. And of course, we don't know how much water was and what type of plants existed back then, but if we were to replace them with the current biofuels, with like wood, coal, and we replaced with wood, bioethanol and biodiesel with different replacement rules, we would get a big number. This is the to sustain the photosynthesis for those plants and to meet the current energy demand. And then we will see that the current energy demand would require as much water as the total terrestrial evapotranspiration, which stresses the fact that this is just a thought experiment to show that the global water cycle doesn't allow to sustain the current energy needs with fuels produced by current water on the planet. And so the replacement of fossil fuels by biofuels can never be total, complete. We need to look at other forms of renewables that are not fuel-based. And the other thing is that we use implicitly water from the past to sustain our current energy needs. Then the same analysis can be done in terms of land, and there isn't, if we replace the if we were to meet the current energy needs of the Western Europe, which is a compromise between developing countries and the United States, and also the food needs, we can with existing cultivated land, and we were replaced seeing fossil fuels with different levels of replacement from 10% to 100%, we can show that the population that can be sustained is much less than the current population. Again, this is to stress the fact that this is a short blanket, and water plays a major role in limiting, or is one of the metrics we can use to show how short this blanket is. There's been an interest in recent years in shale oil and gas. Many of these deposits are in water-stressed regions of the world, and so in pink are regions where the exploitation of these deposits would lead to some competition with the agricultural system. And then also the coal-fired power plants require some water in the production system. Locally, that water can be important. This would be in red areas where water stress exists for part of the year because of the presence of these power plants. And if we were to equip them with the carbon capture and storage facilities, additional water would be needed, which is shown in the pink part of those bars. Again, to stress the fact that water is also needed in the energy system, and some of the climate mitigation strategies require water. I was looking recently at the case of hydrogen. I don't want to bore you with these different systems of production. Each one of them is even just by splitting the water molecule, it means that they need some water. But if we are going to use it for the energy from fossil fuels, we would need to, and we are going to associate that with carbon capture and storage. Additional water is needed. If we are going to use renewables, of course, would be less water. But even the idea of using biomass to produce hydrogen, and this would be the biomass gasification, would require water because that goes into the production of that biomass. Going back to food, the increasing demand for food can be met in two different pathways, and of course it's going to be a mix of these two. We either expand agriculture at the expenses of natural ecosystems, and this causes a loss of natural habitat, carbon emissions, and loss of biodiversity, or we can intensify production on areas that are currently cultivated. And many times ecologists have been advocating for this second pathway. Apparently also Lincoln did. And because, of course, it has less impact on the natural habitat. We did an analysis and we calculated how many more people can be fed by closing the yield gap, the gap existing between the current and the potential yields. And we found that it would be around 4 billion people. But most of this yield gap analysis don't account for water limitations, because to close the yield gap, many times you need to add fertilizers and irrigation. And not always there is enough water to make it happen. So we looked at the opportunity to expand irrigation in areas that are currently rain-fed. And as we have seen before, in the currently irrigated areas, we checked whether this would be sustainable or unsustainable from the point of view of water needs. And so we looked at, and in green, we see these regions where there is enough water to sustainably expand irrigation, which means without depleting environmental flows or groundwater stocks. This means that the areas, not all areas of the world that are cultivated can be suitable for irrigation because there isn't enough water. This brings for those 4 millions to 2.8 billion 2.8 billion people. And then if we remove all the areas that are currently unsustainably irrigated, we go down to 1.8. This is, of course, we can challenge these names, these numbers, because these are based on annual data, and so we would need to see if the water is available in the growing season. Otherwise, some storages are needed. We will see some results later. But this is just to stress the fact that water plays an important role in limiting the ability to produce food and to sustain the increase in demand. Of course, the other approaches would be to work on the demand itself and find less reduce human demand of agricultural products. Then the other point I wanted to stress is that the water scarcity is different from drought. And again, this is a pretty obvious thing, because drought is an anomaly with respect to mean climate conditions. Scarcity is also determined by human demand. And I want to say in this, throughout this talk, I find many times what I talk about are things that my dear friend and colleague Mesfin McConnell has been working on that a long time before me, and this is an influential paper that he wrote on, and cited here, and many other parts of this, his work intersects with what I'm going to present. So it shows basically that it's interesting to combine human demand with availability. And where we have a condition of scarcity of blue water, means that not all the land, from an agricultural point of view, can be irrigated, which was shown in the previous picture. And this is where competition for water may happen. This is where also conflicts for water can happen, as we have done in this study in Central America, trying to connect the dots between some urban conflicts in Central America and water availability for food production. An interesting thing is also to look at climate change scenarios. Here we compared what is in the baseline conditions around the year 2000 and what would happen in a world that is warmer by 3 Celsius degrees, looking at changes both in demand and availability of water. And so we see that in blue are areas where irrigation can be expanded, but can be expanded by adding some storages, so that seasonal storages of water. And in pink, instead, are areas where irrigation can be expanded without requiring storages. One thing that we see is that we compare the two maps. There is much more blue and less pink in the climate change scenario, meaning that some areas can be irrigated also under these climate change conditions, but they will require more storages. And this is shown in this picture here, the trade-offs between areas for irrigation expansion with without storages. So with storages would be in blue. And then and so storages by themselves are very critical, because there is a political capital that needs to be spent for the construction of dams. They are very controversial because of the environmental impacts, mainly the trapping of sediments, the relocation of people, and appropriation of land, and strong environmental impacts. And so there is interest in recent years in older ideas of storing water below ground, so using aquifer recharge and managed aquifer recharge as a way to store water from the rainy season and use it during the growing season. This is becoming critical, for example, in California, where there is also a shrinking of the snowpack, which is a natural water storage. And so this study I always present is by the Public Policy Institute of California, or they synthesized some data showing that the amount of water storage below ground in the Central Valley is so many squares while one of these squares is the surface, what can be stored now in surface water reservoirs. So there is a strong potential there. Again, this is important to remind ourselves that we live in an interconnected planet. I was stressing before how trade has been increasing over time. So we studied the trade of food commodities in terms of calories, and this shown in these top figures. We see that over the last 40 years there has been an increase in intensification and globalization of food through pathways of trade that involve more and more South America. This could include, for example, the famous trade of soybeans from South America to China as a feed for the livestock production in part. And there is much more interdependence, which allows some parts of the world to depend on water resources that exist somewhere else. This is something that was understood by Tony Allen, who came up with this idea of virtual water trade. The idea that some regions of the world have a chronic water scarcity, so basically based on their domestic food demand, there isn't enough water to feed everyone, typically North Africa and the Middle East. This is possible because of flows of grain and other food commodities from other parts of the world. So that flow was interpreted by Allen as a flow of virtual water. Virtual because it's not physically present in the grains, but virtual because it went into the production of those grains to stress the global interdependence between consumers and water resources existing on the other side of the world. Again, this is something that was quantified with meticulous work and extreme detail by Matthew McConnell over the years, and he developed databases that have been helpful to advance research in this field. And then other mechanisms of globalization of water can be through the global investments, particularly investments in agricultural land, which have increased since the last few food crises of 2008 and 2011. The phenomenon that of land appropriation, land acquisition, that sometimes is called land grabbing when it happens under unbalanced power relations between the population that live and used to have control of that land before, and the investors. Associated with these investments, there is an appropriation also of water resources, and we will talk more about this later. So this overview reminds us of four major things: that the human uses of water are strongly globalized. They are affected locally by water scarcity. They are mainly for food production. And so there is a nexus between water security, food security, and then also human rights. So there is a way to refer often to the human right to water by referring to the human rights to water and sanitation, which is of course very important. But there is also another human right to water that goes through the human right to food. To produce food, we need water. And so that's, I would say, more critical in a different way, because we need much more of the water to produce food. So, and so we could have serious conditions of scarcity to deal with. So the challenge is whether water should be considered as a good or as a human right, and also what are the mechanisms of access and appropriation of water. And then the other thing is to relate concepts of sustainability to justice and inequality. And these are very ambitious topics, so we can only scratch the surface today, and are also topics of active research. But first of all, we can look at different human uses of water. It can be done for the production of food, so they are pretty much related to the human right to food and water that is associated with that. Or can be water used to sustain some other economic activity. This I'm showing mining, but it could be other activities. And so there are behind that some commercial water rights. Then we have nature itself. To function requires water. And so when we are talking about the environmental flows, it's a way to recognize some rights to nature to have access to water. And in recent years, so there's been this notion of the rights of nature assuming that stressing the fact that nature can hold its own rights in the same way as human beings can hold human rights. And this whole literature on rights of nature is strongly inspired by also philosophy and ways of relating to nature that can be found in many indigenous groups around the world. So we can think of different conceptions of water as a natural entity, and so putting nature at the center, it would be a more ecocentric perspective, or instead more from the point of view of humans, with a more anthropocentric perspective, as water used to fulfill human rights, as a resource to sustain some economic activity, or as a commodity, water becoming itself the object of some financial speculation. And so there are different functions in this way. One is for habitat, the other one would be for water and food security, subsistence and production, and speculation and profit. This is associated with different sets of values. An intrinsic value of water as independently of humankind, or an extrinsic value as a function of water being instrumental to some human needs, which could be today's needs or future needs. And then we can look at different legal disciplines that go from the rights of nature to human rights to the so-called future person's rights, which is a way to look at questions on sustainability. And then we can go to access and property rights, or really private property rights, where there is a title that can be traded, exchanged, and sold on the market. And again, we have different interests that can be nature, can be all human beings, future generations, stakeholders, or shareholders. With this, I tried with this table to summarize different things that we can see in different literature that goes from the more legal scholars to the concept of values that can come from environmental ethics and also economics. And we can start first at the competition within the human system between water for food or water for other activities. And this brings us to this question of whose water. So there is an emerging field of study that is called water tenure that tries, is very similar to what we would define as land tenure, the relationship between people and water resources. And these relationships can be legally or based on legal arrangements or on uses. This leads us to identify a bundle of rights on water, which can be associated with a title of private property on water, or can be associated even just with a concession to use water, or a right to use of different types. And so there would be rights to use or not to use water, in the sense that if I don't use water, I don't use that right, to transfer the right to use, to exclude others from excluding uses, to have some right to be part of the management of water resources, or to appeal decisions that are given made by a water authority. So this is defined in general as a bundle of rights, similarly to what is done in the case of land rights. And the interesting part here is that depending on the type of water tenure, the transferability of rights can exist or not exist. And this transferability is crucial to create conditions that would lead to markets, and depending on whether the rights can be sold or traded. And so the process of commodification is the process that converts a natural resource from being a natural entity into something that is fungible and good that can be traded and sold. And in a book on by David Harvey, he uses this sentence that I found interesting. Every society sets boundaries on where commodification begins and ends. And I think water is really at that boundaries, because depending, was last year doing a sabbatical at the FAO in Rome, and so I did a comparative study, and we can see different countries, different parts of the world treat water in a different way, more as a commodity or as a natural entity. And so the water tenure sets the norms and institutions that regulate, establish who can use water. This is one thing, but then we can have, independently of that, some water claims who can go and say this water is mine. And third, we can have people who physically control water and access to water resources. Sometimes these three things are not aligned, and you can have that the right to use is with one group, and then the possession is with another group, etc. These are conditions that can lead to water appropriations and water grabs. So one thing I'm going to do now is to look at physically what are these mechanisms of appropriation. And so one way to appropriate water is by buying land that is over a good aquifer or adjacent to a river, and to have direct physical access to this water resource. Another way is to build an infrastructure. So whoever drills a well basically becomes the gatekeeper and controls access to water and can exclude others by pumping a lot of water from that well from having access to that water. And so, similarly, a dam, by building a dam and creating a reservoir, someone gets more of a control on that water resource and decide how can be that water resource can be assigned or used, and can also exclude others from having using that water. By polluting water, downstream waters, inevitably we make it unusable to other people, and then also. Not only we make them unusable, is that we limit the ability to withdraw that water, because at some point the concentration of pollutant becomes unacceptable. So this is a major way to control downstream uses. Then by planting water-dependent crops or forests, and we will see more about that. Then through land use changes, we can affect one land use change in one place can affect precipitation somewhere else. Of course, it's much harder to document this this link. By adopting systems of irrigation that are more efficient, we reduce the return flows, and or by controlling energy supply. So let's go quickly through. I would like to focus on some of these because are more interesting. Land acquisitions, many times, particularly land investors who invest on large pieces of land around the world, mostly in the global south and in Eastern Europe, tend to focus on areas that have a preferential access to groundwater or surface water. So, or less green water scarcity. Green water scarcity means that the precipitation is not sufficient to meet the irrigation water requirement, and the input of water as irrigation is needed. Let's look at the infrastructure. By, again, building a dam, downstream users don't have access to that. So we did a study for about 10 to 20, I think, major dams in this paper. They were built in Africa since the year 2000 for irrigation, for agriculture. And we looked at the emergence of irrigation schemes, would be something like this. Then with some algorithms, we were able to determine the size of the land parcels and compare the size between before and after, if it was irrigated before. And what we see that is many times these dams and these irrigation schemes are to the benefit of large-scale farmers, so mainly large agribusiness. And so dams are often not built to the benefit of smallholders. And so this is, again, one example that has been strongly discussed is the case of the Omo River with the Gibe 3 dam that excluded the downstream population from having access to water, and causing also having some impact on the aquatic habitat of Lake Turkana, which is also in Kenya, and so there is also a transboundary issue here. And many times it's for large-scale farming. So it's a way to appropriate water resources by land investors to the benefit of foreign users and at the expenses of local farmers. Then afforestation projects, there is a lot of excitement about the idea of nature-based solutions to climate change. And so, of course, planting trees is always politically a very appealing proposition. But of course, there is no free lunch. So by planting trees, because this is part of the first class of forest hydrologic course, we would say that by planting trees we have a decrease in runoff, so downstream users lose access to water resources. In this study we looked at the increasing water scarcity in areas where some of the afforestation projects would be feasible, based on this paper by Bastin, that identify areas of possible afforestation or tree restoration potential. Again, this is important to remember that this is also creates some questions of environmental justice, in the sense that the climate change, which is caused by emissions by the global north, done at the expenses of water resources in the global south. So there needs to be some sort of compensation, or some awareness at least of the impacts of these approaches. Then we see there is also this idea, and this is not my work, it's the work by Abby Swan at the University of Washington. She looked at how different scenarios of forestation could affect precipitation somewhere else. This is also an interesting idea that shows how we can modify, and this is an issue of water tenure, water availability in other parts of the world. And so there is a group of scholars that looks at this more, looking at trajectories. The work by Pat Key at Colorado State. He argues that clearly precipitation in a certain area, let's look at the area in the middle there, is contributed by moisture coming from different sources, from evaporation from the oceans, from evapotranspiration from that region itself, and also from evapotranspiration from surrounding regions, which means that by changing in the surrounding regions the land use, we can affect precipitation in the central point. And so we can have not only interdependencies, but also some impacts on water resources. And there are some groups that are actively studying this. Of course, it's very hard to document, and there are many uncertainties, but I think it's an interesting idea. I no need to talk much about pollution. Mainly, this is a framework, and again, Mesmin McConnell has been a leader in this. That is the framework of grey water footprints that allows us to study the impact of pollution. Basically, we need a certain amount of water to dilute a pollutant. That water needs to remain in the stream, it cannot be withdrawn. So by polluting the stream, we prevent downstream users, limit the withdrawals by downstream users. Otherwise, the pollutant would become too concentrated. Then I was talking about irrigation efficiency, because there is always a lot of interest in the idea of increasing the efficiency of irrigation. And there are basically three irrigation technologies. There are more, but we can summarize them in this way. The surface irrigation, where we flood the land, or we have furrows and flood the areas in between. And or we can have sprinkler irrigation, like an artificial rainfall, or drip irrigation, very much localized. They have different efficiency. The efficiency is represented by the ratio between the water used by crops, so the consumption through evapotranspiration, and the withdrawals. And again, a more efficient system has a higher fraction of the water that is actually used by plants, which means that the return flows are smaller. So clearly, at the farm scale, a more efficient system uses water better, but in larger areas, this means that there are less return flows. So if we control assign water permits in terms of withdrawals, and the farmer has a permit to extract 100 units, in the farmer, before switching from surface irrigation to drip irrigation, used to release downstream and to the groundwater 50 units. Now the farmer releases only 5 or 10 units. This is the reason why some areas that have adopted the drip irrigation saw groundwater depletion. And this phenomenon has been defined as the irrigation paradox. From the point of view of water tenure, there is a big issue here about whose water is the water in the return flows, and whether farmers should on the return flows, or there should be some regulations on the return flows because of the phenomena we have been talking about. But in general, I think it's important to remember that by switching to changing system of irrigation, we have an appropriation of these return flows. And now, to complete this picture, we can go back to this interaction between humans and nature. And now we can look at the water as a human right or water as a natural entity. Really, to meet the human right to water, humans need to appropriate a certain amount of water. At the same time, the environment needs to have a certain amount of water to function. And this has been defined in different ways, but more recently, in the last 10 years, the notion of planetary boundaries became very popular. So the planetary boundaries identify the amount of resources, the amount of environmental impacts that humans can have on the environment before having detrimental impacts. And so there is a limit to human appropriation of nature of water resources that are imposed by meeting the human right to food, which means that the water consumption needs to be, and we can make it simple, greater than the number of people on the planet, the minimum amount of water that is needed to feed one person. And since we know that there are inequalities that in types of diets, also in opportunities to having access to resources, we need to account for the existence of these inequalities. There would be a factor there, this factor phi. So this is the minimum amount of water that is needed, or close to the minimum that is needed to feed every human being, which is, again, this is just a thought experiment. Then we need to also respect the planetary boundaries. The planetary boundaries, the only way to calculate them is to have a spatially distributed approach. In each point, and we focus mostly in each point on Earth, we can look at the local water consumption needs to be less than runoff minus environmental flows. The water consumption includes also, is dominated by consumption for food production, but includes also other local needs including drinking water and other activities. And so you see that overall, we need to combine these two conditions. To meet the human rights, the consumption needs to be greater than a certain amount. To meet the rights of nature, the consumption needs to be less than a certain amount. And what we are going to do now is to see how short this blanket is. But at this point, we know that the environmental impacts are local constraints. Locally, this condition needs to be met. But instead, the food system is so strongly globalized that we can look at that as a global constraint, because through trade, we can redistribute water resources. And so if we do this, we did this in this paper, we can, with the same modeling approach I presented at the beginning, we can determine a floor for minimum water appropriation of water, which represents the human right to food, and the ceiling, the rights of nature, so the planetary boundaries. And we start with one scenario in which we take, I use here the the shared socio-economical pathways that are used by the IPCC. These are scenarios of socio-economic development. And we look at different types of environmental flow scenarios. What has been often used by the planetary boundary communities is 80% of local runoff would be considered as the environmental flow. We see that if we take the most sustainable scenario, we have the floor below the ceiling. And the most sustainable, here we have also three different scenarios of population growth. And this is the low population growth with the economically most sustainable scenario. Economically most sustainable scenario here plays a role through the consumption of meat that is a major contributor to the human footprint of diets. Now we can go to a medium population growth scenario. Already the floor approaches the ceiling. High population scenario means that we have the floor above the ceiling. So in this population growth scenario, we would be exceeding the planetary boundaries. And now the only way we can do, which is what often also regulators do, we can change the environmental flows. We can say we are happy with the 20% of environmental flows, and this would increase the ceiling. Of course, this is with some environmental cost. Of course, we cannot go with less than 0 environmental flows. But you can see how by changing socio-economical pathway and a medium population growth scenario, the floor is getting very close to the ceiling. And then, of course, if we don't even put the most unsustainable socio-economical pathway, the number 3, SSP3, because that exceeds the ceiling completely. So again, take this as a thought experiment to stress how water constrains the enjoyment of the human right to food. Of course, there are other approaches that can be more in the working on the consumption side, and there is a lot that can be done. First of all, pathways of approaches of sustainable intensification. We can try to think to expand irrigation to rain-fed areas, and then plant crops that are more suitable to that area. So it means planting the right crop in the right place. There is some room for improvement. And then also techniques that allow to reduce evaporation. We can be hydrologists again for a moment. We know that the evapotranspiration, while transpiration is productive loss of water, evaporation is not very productive, so we can have, through cover crops and other approaches, reduce these losses that are not productive. And then other approaches instead are on the demand side by reducing food waste, changing diets to less animal products, and diets were already accounted for in some of these pathways. And then these approaches that are more based on a circular economy of food. For example, we can use some of the stovers from crops as a feed for livestock, or we can use other approaches that try to reduce some of the outputs from agriculture. Of course, these are all based also this idea of degrowth and the idea of not considering the fact that we live in a planet with finite resources, so we cannot think of having an unlimited growth. There have been some models of production, like the aquaponic systems combining aquaculture with hydroponics, or the use of insects as a way to recycle food waste, to grow insects that can be used for feed for animals, recycling water in treatment plants that allow to recover some of the water, as well as fertilizers. There is also the other approach instead is to find the so-called new water. So by treating water, that's already a way of doing this. Or reusing somehow the production water from oil extraction and mining, or which would also require some treatment. But the most, what is already happening is desalination. So through desalination, historically is not a new thing, but historically has been only for water supply, not for irrigation. Now the cost came down enough to become possible, and I know that already in Israel this is happening. Saudi Arabia is moving that direction, and also in California there is some discussion about the use of irrigation water, desalination water for irrigation. Of course, there is also the issue of energy and sustainability from that point of view, whether it can be done with renewables or not. But just to see physically, we did this study to look at the value generated by irrigation water in agriculture. And of course, on average in the world, it would be 13 cents. But this includes the staple crops. But if you go like to fruit crops, is more than $1 per cubic meter, and the cost of desalination is, as far as I know, there are some claims that it went down to 25 cents per cubic meter in some places, but even just 50 cents would make it interesting as an opportunity. Then in conditions of water scarcity, we have the value already paid by the oil industry for water resources, and it's reported there are above $1. which means that at least for in that sector, they already would be willing, and they've been doing this through water markets, so they would pay also for desalination as a possible opportunity. Of course, it has major issues, particularly what to do with the brine, particularly if you are in an inland area, because you don't know where to dump, and even there have been different ideas. So some conclusions, and I might have been running out of time. So we see that, well, the premise of this talk is that life, human development, and the global economic system depends on water, and there is a connection between water for food, energy, and the environment. And there is also that model had a parameter phi that represented inequality. If we increase the inequality, we can see how inequality comes at the expenses either of food security of other people or of the environment, so we can say of justice or of sustainability. And so and seldom inequality or equality is considered as part of an analysis of sustainability of our societies. And the other thing is that there is the human right to the fulfillment of human rights requires water and can be in competitions with the rights of nature. And with this, I really thank you for your attention, and I'm ready for some questions.